honored algebra students, Mr. Lawrence here, and we're going to be talking about vertical motion today. Now, I don't know if you realize this, you probably do, but things don't fall faster because they're heavier. No, they do not. No, Kyle, I'm sorry, they don't. I can't remember if I've demonstrated this in class or not, but I thought we would travel to the moon today. Now, you must understand that we are neglecting air resistance, and there is no atmosphere on the moon, so that's the best place to test this. But let's watch. An astronaut from Apollo 15 is going to drop a feather and a hammer on the moon at the same time, and let's watch and see what happens. So it's only about a minute long. Let me get it playing here.
Jim, we copied both solar wind and penetrometer drum in the ETB.
All right, so here comes the astronaut.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
All right, so there you saw it yourself. The hammer and the feather fell at the same rate. That's true of everything. If you're not sure why when you drop a piece of paper or a bowling ball, the bowling ball seems to fall faster, it's all because of air resistance, okay? Everything falls at the same rate. And we actually have an equation that tells us the rate at which everything falls here on Earth. There's equations for other planets, but it all depends on the gravity, okay? H, this red H here, H is your ending height, the ending height. And you're thinking, well, that's the ground. Well, depending on the problem, it might be, but it's the ending height, okay? Could be the ground. All right, T, of course, you already know is time, right? T, that's time. And there's two T's in the equation. One's being squared, and one's just a T to the first power, but they're still both time. So, you know, if the time is 5 seconds, then it'll be 5 for both the T's. Okay, let me see here. V sub O, that stands for original velocity or initial velocity. Original velocity. You know how we might designate numbers, you know, like x sub 2 and then x sub 1 comes before it. Well, what would come before that? Well, x sub 0 would. So this is V sub 0, original velocity. And you should know that velocity is both speed and direction. Finally, S is your starting height, the starting height, okay? Now, this is like really cool stuff, and these problems are so flippin' simple. It's like a wonder nobody knew how to do them until Galileo and Isaac Newton, etc. Okay, so let's check this out. So it says a baseball is thrown from a height of 10 feet off of the ground with an initial velocity of 25 feet per second. Okay. A, we want to find out how high off the ground the ball will travel. B, how long will it take to reach its maximum height? C, when will the ball be 30 feet off the ground? And D, when will the ball hit the ground? So the first thing I'm going to do is I'm going to write this formula down. I'm going to write it down a whole bunch of times when I do my homework. That way I'll memorize it. I don't have to memorize it separately. Okay. Now, you might be wondering, why is there a plus or minus in the middle of the formula? Well, it depends on if the initial velocity is going upward against the pull of gravity or downward with the pull of gravity. Gravity is pulling downward at a rate of 32 feet per second squared, or 9.89 8/10 meters per second squared. So up is positive, down is negative. Okay? Now, I'm going to draw a picture. Always going to draw a picture. So I've got this baseball, you know, somebody's holding a baseball, right? okay, and the baseball is 10 feet off of the ground, okay, when they release it. So they're throwing it upward, and we know that that's 10 feet. Now, you might not realize this, but the ball is going to travel in a parabola. If we were in the classroom, I would model this for you very well. Other than dropping it straight down or throwing exactly straight up, it's pretty difficult. That's the ground, by the way. It's supposed to be level, but with the airliner, it's a little tricky. It's not possible, unless you're throwing it straight up or straight down, to throw a ball and not have it travel in a parabola. You might not see the whole parabola, the entire parabola, but you know, like you baseball players, the coach says it wants a nice level throw. No such thing. The second the ball leaves your hand, gravity starts to pull it downward. Okay. Now, the harder you throw it, the faster you throw it, the less time gravity has to work on it, so it doesn't curve as much. But it's impossible to throw it straight across. If you're trying to throw it at my chest, you know, my numbers, like the coach might say, you have to aim for a little bit higher because gravity is going to pull it down. If you aim for my chest, it might go to my waist or my knees or something like that. Okay, the first question they ask is, how high will the ball go? All right, so they want us to identify this point here. And we should know that that point is the vertex, right? The vertex of the parabola. Now, the vertex is going to be made up of two coordinates, x and y, right? Input and output. Except in a problem like this, it's going to be made up of t and h. So if we find the vertex, we're going to find out how high the ball goes, and we're also going to find out how long it takes to get there. That's the t part of the equation. That's part b. All right? You remember, independent variable is x, but t, time, is always the independent variable. We've talked about that. All right, so I'm going to set up the equation. H is going to equal negative 16 t squared plus or minus v sub o. Well, v sub o, what was the starting velocity? I want to say it was 25 feet per second. And you know what? It's not going to be 25 plus or minus. It's just going to be plus because the ball's being thrown upward. Okay, the starting height is 10 feet. Now, I'm going to identify A, B, C. Easy as negative 16, 25, 10. And to find the vertex, I normally use x equals negative b over 2a, right? That finds me the x coordinate of the vertex. And then I have to go and plug that in to the equation to find the y coordinate. Well, the same thing, except I'm going to be finding the t coordinate, the time, and then I will plug that into my equation to find h. So I'm going to do the negative of 25 over negative 32, and I'm going to go ahead and use a calculator, and I'll round to the nearest tenth, but when I substitute in, I won't round to the nearest tenth. In fact, hold on, let me pause the video a second. Okay, I think I'm recording again. Yeah, and I've got my graphing calculator up here. I'm going to need it in a minute. Let me get some screens ready to go here. Things were acting a little funky for me. Okay, so I'm going to divide negative 25 by 32. Okay, of course the two negatives are going to cancel out, so 25 divided by 32, and that's going to get me that many seconds. Now, when I report my answer, I'm going to go to the tenths. Well, I'll probably go to the hundredth place. But when I do my calculations, I'm going to use that big, long, ugly decimal. So I know that t is going to equal about, I should do this, t is going to be about 78 hundredths. I believe that's, James, keep your voice down, please. 78 hundredths of a second, okay? But when I go to do my calculations, I'm going to use 78125. I'm going to use that whole decimal. All right. So now I just answered part B. I know it's going to take about 78 hundredths of a second for the ball to get up to the maximum height. To find the maximum height, I'm going to do negative 16, and then I'm going to use that 0.78125. It's got to be squared. My initial velocity was 25, I think. And then again, I need the time. And then the starting height is 10. Okay? And there we go. It's going to go just a hair under 20 feet. Yeah. So for part A, I know it's going to go about, what did I get, 19, what is it, 7600ths, I think? 7700ths, if I round it properly. 600 feet off the ground. Okay, and then how long will it take the ball to reach its maximum height? Approximately 78 hundredths seconds. So a little more than 3/4 of a second. Not very long, okay? Now, this is really cool. This formula is so powerful. When will the ball be 30 feet off the ground? Well, I know it's going only 19 feet off the ground, right? Not even 20. So that's not possible. It can't go that high. So I would say it would never be. But I'll tell you what I'm going to do is I'm going to change that number there because I want to show you a problem that you can do. And so let me make this 14 feet off the ground, okay? And this is where it gets really cool. Had it stayed the way the problem was, you would have said it will never be 30 feet off the ground, okay? Because the maximum height wasn't even 20 feet. But I changed the problem to this, okay? So, same picture. We need to find when will the ball be 14 feet off the ground. So maybe here. The only thing is, it's going up, it's up at 19 feet, a little bit over almost 20 feet, but then it starts coming down. It's going to hit 14 feet again. And here's the cool thing. When you do the quadratic formula, oftentimes there's two solutions, right? The quadratic formula is going to give us both of these solutions. Yeah, it's going to give us this time. Okay, maybe I'll call that t sub 1. And it's going to give me this time, I'll call it t sub 2. It's going to give me both of them. I think that is just so amazing. So, let me see here. My formula is h equals negative 16 t squared plus 25t plus 10. But if I'm looking for when the ball will be 14 feet off the ground, that's the h I care about. So I'm going to put 14 in there. And so now I have this equation. And now I want to solve for t. And since it's a quadratic, I usually want quadratics to equal 0, so I'm going to subtract 14 off. And when I do that, I'm going to get 0 equals negative 16 t squared plus 25t minus 4. Okay, now I could try to factor this. I could try to complete the square or something like that. I find with these kind of problems, if I notice something, like, you know, maybe there wasn't a 4 here, maybe it was a 0 here, I might factor it out by GCF, and it's really quick to do. But usually I go with the quadratic formula. So I'm going to go A, B, C. Easy as negative 16, 25, negative 4. Okay, and I'm going to find the discriminant right away, the b squared minus 4ac. So I'm going to do 25 squared minus 4 times negative 16 times negative 4. So this should be 625, and this would be 16 times 16, right? So it should be 256, right? All right, so I'm going to subtract. And let me see here. My answer is going to be 300. It can't be 7. It's going to be 6. I believe that's right. Check me on that. Just make sure, because if I have a mistake, it's going to make me look silly. Yeah, 369. Very good. Okay, so that's my discriminant. So now I'm going to go t equals the negative of b plus or minus the square root of the discriminant all over 2a. Okay, and now I'm going to go to my calculator, and I'm going to be really smart about how I use this. I'm going to do it all in one step. Okay, so I'm going to have the numerator is going to be negative of b plus the square root of 369. Oops, sorry about that. Okay, and then I have to close that parenthesis, and then I'm going to divide it by negative 32. Depending on the type of calculator you're on, you might want to just do the numerator, or just and then do the denominator and divide, or you might need an extra set of parentheses. Okay, on mine it works just like this. And there I get about 18/100ths of a second. So that's when the ball is going to reach 14 feet the first time on the way up. And it makes sense because it's not a very long period of time. It's going from 10 feet to 14 feet. It's going to hit it pretty quickly. Now, the cool thing is, to get the other answer, because I'm on that graphing calculator, I don't need to do a lot of work. Okay, and this is going to be an and because it is going to hit it at both times. So now I'm just going to go second enter, and I'm going to change that plus the square root of 369 to minus the square root of 369. And now I'm ready to, boom, there it is. There's the other time, and it's longer. Yeah, it's actually pretty cool. Oh, shoot, I forgot it. I think it was 1 in 38/100ths. Okay. Okay, 1 and 38/100ths. Okay, now we always want to answer in a sentence. So for part C, we would say the ball will reach 14 feet in about 18/100ths seconds, and again at 1 and 38/100ths seconds. And there you go. All right. Now, the last part of the problem is, when will the ball hit the ground? That's part D. Well, that's an easy one. We take the same formula we started with. So we started with H equals negative 16t squared plus 25t plus 10, and we make h 0 because the ending height, it's on the ground. How many feet off the ground is it? Well, it's 0 feet off the ground. Okay. All right. And now I'm just going to use the quadratic formula again. So t is going to equal negative 25 plus or minus the square root, and I'm going to figure out the discriminant right away here. 25 squared minus 4 times negative 16 times 10. And it looks like the square root is 1,265. 1,265. And that's all over negative 32. All right, so t, and I'm going to get two answers, but one of the answers is going to be negative, because look at my parabola. Look at my parabola. Okay, it doesn't start at the ground. No, it starts above the ground. So if I continue this parabola backwards, something like that, haven't I traveled backwards in time? Right? So I am going to get this negative root here. I'm going to ignore it, but it's just so fascinating because it's as if the parabola is there even though only part of it is. It's pretty amazing stuff. The math geek in me just gets so excited about this. All right, so let me go back to my graphing calculator. I'm going to do, let's see here. Nope, wrong button. What do we got? Negative 25. Oh no, it's not going to like that. It's not going to like that. The calculator thinks the negative and minus are two different things. I'm going to want the negative one because if I use the positive one when I divide by a negative, I'm going to get a negative number, and that's the time I don't care about. I care about the positive time. All right, divided by negative 32. And there we go. So about 1 and 89/100th of a second. Okay, so 1 and 89/100th seconds. And of course I should answer in a sentence. All right, that's a sample problem. You're going to be doing stuff like that tonight on the homework, all right? Please ask questions. Please send me emails. I would love to assist you. Mr. Lawrence signing out. Have a good night, everybody.